Hello, sir. Assalamu alaikum.
Walaikum Assalam. So,
How are you, sir?
so yesterday basically in the last class we talked about the numerical differentiation. How can you differentiate numerically a function? And we told that there are three methods: Taylor's method, Euler's, and Runge-Kutta method. So now today we talk about the Taylor's method. So before than that, I have to say that we have just 2 weeks left. That's mean this week and the next week, and then our final exam will be started from the 18th September. So we just have uh, 2 weeks left. So now we talk about the Taylor series method. The Taylor's method basically is called the Taylor series method for differentiating the function numerically. So first of all, we just know the methods how to do these things, and I already told you that what types of differentiating problem we can solve. We can only solve ordinary differentiation. That's when ordinary differentiation of only one or two variable we can solve with this method. So the form actually, first of all, you have to define the form. The first method we are using, that is Taylor's method. In this method, form of the differentiation, that's mean what types of differentiation, what types of problem we actually can solve. That is the form of the function. Okay, so okay, we need some correction basically. Basically, the topic is not numerical differentiation. Basically, it's the topic of numerical differential equation. Okay. So numerical differentiation is actually something different than the differential equation. Okay, so let's check. Okay, just wait a bit. I just check the book. So which book you are actually studying? The book of Shastri, isn't it? Hello, are you listening? Hello.
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay, so let's check the book actually. Okay, so there is some correction. Okay, so in the previous topic we talked about the numerical integration. You remember this? In numerical integration,
Yes,
we
sir.
are using
Yes, sir.
Yes, sir.
three
sir.
formula we are using, that is trapezoidal rule, Simpson 1/3 rule, and Simpson 3/8 rule. And I told you that the next topic is numerical differentiation, but um, at this moment, numerical differentiation has a method, but I told you that there are three methods for numerical differentiation. This is actually not correct. This topic basically, or these three methods basically for solving numerical differential equation. That's mean how can we solve differential equation numerically? That is the three methods. This is Taylor's method, Euler's method, and Ranjivata method. These are the method for solving differential equation, not that numerical differentiation. Okay, so there is a little bit difference. So the topic numerical differentiation, maybe I'll talk you in the another class, maybe end of this topics. So this topic is not numerical differentiation. There is actually numerical solving numerical differential equation. Okay, so this is the result. Or you can say that numerical solution of ordinary differential equation. That is actually you can say that.
Sir,
Yes.
sir, are you writing?
So we
Sir?
can see your writing, sir, on the screen.
Yes, sir.
You don't see my screen?
Yes, sir.
Then maybe
Then-
so you were presenting another person.
Yes.
We didn't see you have your writing.
Okay, I'm sharing the screen again. Now you see?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes.
It's okay now.
Okay, sir.
Yes, sir. Now it's okay.
So there is a little bit correction. So what we discussed in the last class, that is actually true for the numerical differentiation. That's mean there are two types of numerical. There are two types of differentiation: ordinary differentiation and partial differentiation. And we know actually the difference between ordinary and partial differentiation. We already discussed in the last class. And the topic for numerical differentiation I will teach you after that topic, after this topic. Okay, so topic I changed for this class. The topic is actually how can we solve a differential equation numerically. So numerical solution for ordinary differential equation. So the differential equation also two types, because of differentiation is two types, ordinary and partial. So for the same way, differential equation is actually there are two types: ordinary differential equation and partial differential equation. So this is the ordinary differential equation and this is partial differential equation. So there are two types of differential equation, like as the two types of differentiation: ordinary differentiation and partial differentiation. Same as for the differential equation, that is ordinary differential equation and partial differential equation. So in this case, we just only can solve ordinary differential equation. Okay, so for this topic or for this course, we are solving ordinary differential equation, not the partial differentiation. Okay, this is we cannot solve at this moment. This is for the another course. So methods for numerical differential equation. So how can we solve the differential equation numerically? Which method we have to use? There are three methods. There are many methods, but I'll discuss in this course only three methods: Taylor's method, Euler's method, and Ranjigata method. Okay, so something I changed in here. So first of all, you need to understand the change. So what is our topic? Our topic is how can we solve differential equation numerically, or ordinary differential equation numerically. You understand this point? What are actually we are going to do? We are actually solving ordinary differential equation numerically. That's when we are talking about the numerical methods for solving ordinary differential equation. So there are three methods: Taylor's method, and Ramsey-Cotta method. So these three methods are using for solving ordinary differential equation numerically. You get this point?
Yes, sir.
Okay, so before than that, you have to know what is actually differential equation. That is we have to know. What is differential equation? So that's the first question we have to ask ourselves. How to set the ruler. Okay, so the first question is what is actually numerical, what is actually differential equation. So you know differentiation, what is differentiation. So simple way we can answer this question, what is actually numerical differentiation, what is actually differential equation. Simple way to say that If you see any differential operator in any equation, that is actually called differential equation. So I just write it informally. How can we say informally, not formally? Informally.
So in our final term, there is any theoretical question?
I don't know what is theoretical question. So informally, we can say that if there any differential operator is involved in any equation, then it is called numerical. It is called differential equation. So the definition is very simple. That's mean you first of all, you know that what is differential operator. That is actually I discussed in the last class. What is differential operator? That's when if you see ddx, that is actually the differential operator. You know these things, ddx or something like that. So this is the differential operator. ddx. These are called differential operators. So it may be ddx or simply capital D or simply small d, whatever it is. If you see these types of things, then it is called differential operator. And if you see any differential operator in any equation, and what is equation? Equation is just like a simple, what you know, any equation. So like ax plus by plus c equal to 0, that's an equation. So if you see these three things, or in many form, like the ddx, d or d, something like that. If you see any of this operator in any equation, that is called differential equation. That's an ordinary differential equation. You can say that. And if you see partial differential operator, that will be partial differential equation. Is it clear?
Yes, sir.
You got this point? That's when if you see in any equation like that, I am writing an equation x squared plus twice x plus 1 equal to 0. So this is a simple equation. So in that equation, there is no differential operator. But if I am writing any operator in here, like that, this one, so now you see that there is a ddx, there is operator, differential operator. So this equation, you can say that this is ordinary differential equation because ordinary differential operator involved in this equation. You get this point? Hello?
Yes,
You
sir.
get this banana. So this is important. You have to know the basic. That's when this question is first of all important. If you don't understand this one, you cannot understand anything in this one. Okay, so first of all, you have to understand this one. What is differential equation? Because we are going to solve differential equation numerically. And differential equation you can solve by its own method, traditional method. That's method you have to learn in Math 197 course. So there are in that 197 course, there are majority of the part actually discussing about the solving for numerical, solving for differential equation. And there are many types of differential equation, and there are many formulas or many methods for solving differential equation based on the types of equation. But in this course, we are talking about solving differential equation, but we are talking about solving differential equation numerically. That's when we are using numerical method for solving differential equation. You get this point? So if you done this course 197, then you already know that what is differential equation. And if you do not, if you did not do this course Math 197, then differential equation is what? This is I am saying informally that if you see any operator in any equation, if you see any differential operator, that's been ordinary differential operator, ddx, d or capital D or small d in any of the equation, then it is called differential equation or ordinary differential equation. Like this one is ordinary differential equation because ddx is involved in here. You get my point?
Yes, sir.
Yes.
So,
Yes, sir.
so this is so these types of equation basically we are solved by this numerical method. That means this is a differential equation, and these types of differential equation we can solve by these three methods. But there is a limitation also. By these three methods, we can only solve one type of numerical, one type of ordinary differential equation, because there are many types of differential equation, ordinary differential equation. So from all of these different ordinary differential equation, we can solve only one types of ordinary differential equation. So which types of differential we can solve? So we just write it in here from the beginning. We can solve the differential equation Okay, so just give me time to make a sentence. So what is the form? That is the form actually dydx equal to f of xy. So this is the important things you have to know, that what types of differential equation we can solve by these three methods. We can solve only these types of differential equation by these three methods: Taylor's method, Euler's method, and Jacobi method. What is the form? dy dx equal to f of xy. So f of xy is a function. So that's an equation, dy dx equal to f of xy. That's when if you see these types of equations, so we have to, if you find this equation, then we have to convert this equation into this form. Okay, So this is the standard form. This is the standard form for this course. So if you see any types of differential equation, then you have to convert, or you have to actually reshape, or what you are saying. You have to say, you have to remake the differential equation in this way. So you have to convert the differential equation into this standard form. So only we can solve the differential equation numerically for these types of differential equation, not the other types of differential equation, because there are many types of differential equation. We can solve only these types of differential equation. Now you look at that dy dx. So if you see dy dx, that's when you understand x is the independent variable and y is the dependent variable, and we are writing equal to f of xy. So that's mean I am writing this one. If you look at carefully, so you understand I am writing actually this one. Now y equal to f of x comma y. This is I am writing in here. So y equal to f of xy. But normally we have to write this way. We are writing this way, like that. Y equal to f of x, isn't it? That's mean y is a function of x. That means f is a function of one variable. So y equal to f of x. So this is the normal equation. So this is the x is the independent variable and y is a dependent variable. So I am writing y equal to f of xy. That's mean f of xy. When you write y equal to f of xy, that is not means that f is a two variable function. F is not a two variable function. This is actually one variable function. That's mean one variable function means one independent variable and one dependent variable. So when you talk about the equation, there is two variable you need. When you talk about an equation, one is actually independent and another actually dependent. So in that case, x is independent variable, y is dependent variable. But when you write in this form, like this one is exactly like this one. When you write in this form, so that also means that x is independent variable and y is dependent, because y is actually out of the f of xy. So y is actually the dependent variable and x is the independent variable. So similarly, like this differential equation, y is the dependent variable and x is the independent variable. So what does it mean, f of xy? So f of xy means this is called implicit function. So do you have any idea about the implicit and explicit function? We have to
No,
learn.
sir.
We have to learn these things many previous courses like 147 or any other courses. When you talk about the function, implicit and explicit function. So this is basically the implicit function. So that is how we are writing the differential equation as of the implicit form. So this equation I am writing, actually I am writing the equation as an implicit form, not the explicit form. Okay, so this is the function of implicit form. So that's why we are writing f of xy. So this doesn't mean that there are two variable function. This is actually one variable function, but x is independent, y is dependent. How can you understand? Look at this one. dy dx. We are differentiating with respect to x. So x is the independent variable and we are differentiating y. So y must be dependent variable. So this is actually the one variable function. That's when one independent and one dependent variable function. You get this point?
Yes, sir.
So these are the types
Yes,
of
sir.
function we can solve by these three methods. Okay, only these types of differential equation we can solve by these three methods. Other types of differential equation we cannot solve by these three methods. We need another methods. But in this course, we are only talk about one types of differential equation and how can you solve numerically by these three methods. And other types of differential equation we can solve maybe regular or traditional method, what you learn in MAT-197 course. Okay. So we just have 1 minute's time to, so it will be better if you can rejoin. Okay.
Okay, sir.
So rejoin this, because after 1 minute it will be disconnected. Okay, so I talk about that explicit and implicit function. So I just give you an example so you can understand what is explicit and implicit function. So explicit function is just, I just give you an example, then you can understand. That's the called explicit function, y equal to f of x. That's when variable are separated. Independent and dependent variable are separated to each other. That is actually called explicit function. So this is very simple things. So you can write y equal to x squared plus x plus 5. So this is the explicit function. That's mean there are two variables, independent variable and dependent variable. X is independent and y is dependent variable. When you separate this independent and dependent variable, that is called explicit function. That's mean dependent variable equal to in terms of independent variable. That's mean if we can express dependent variable in terms of independent variable, that is called the explicit function. And if we cannot, or if we do not separate the dependent and independent variable, that is actually called implicit function. So implicit function is actually like this form. That is called the implicit form of the function. That's when where the variable are mixing. So you can write y equal to x squared plus 2xy plus square. So this is called implicit function because of y, because of y is dependent variable and x is independent variable. So this is actually the variables are mixing in each other. So you should not write y equal to something. You can write equal to 1 or any other things, or equal to 0, something like that. That's when the variables are actually not separated. Dependent variable and independent variable are not separated. They are actually mixing. That is called implicit form of function. You understand?
Yes, sir.
Hello?
Yes, sir.
You
Yes,
get this
sir.
point? Implicit and explicit function. Explicit function means
Yes, sir.
when the function are separated. When are variables, independent variable and dependent variable are separated. They are not mixing. That is called explicit function. That's when you can say that when dependent variable is expressed in terms of independent variable, that is called explicit function. But when we cannot express dependent variable in terms of only the independent variable, that is called implicit function. That's mean when dependent variable and independent variable are mixing to each other, that is called implicit function. You get this point?
Yes, sir. Good.
Yes, sir.
Hello,
Yes, sir.
I don't
Yes.
get any
Yes,
response
sir.
from you.
Yes, sir.
Hello, are you listening?
Hello. Yes,
Hello,
sir.
sir.
Yes, sir. Yes, sir.
Yes, sir. Yes, sir. We are listening.
Hello,
Yes, sir. We are listening.
are you listening? Hello,
Yes, sir.
Yes, sir. We are listening, sir.
Yes, sir. Yes, sir.
hello.
Yes,
Yes,
sir.
sir.
We are listening. We can hear you.
Yes, sir. We are listening.
Are you listening? Hello.
Yes,
Yes,
sir.
sir.
Yes, sir. We are listening. We are listening, sir.
Yes, sir. We are listening. Hello, sir.
Hello, sir.
Hello.
I'm not sure actually you are listening or not. I don't get any response from you and I cannot listen anything.
Sir, we
Hello,
are.
sir.
Sir, we can hear, sir. You carry on.
Hello, sir.
Sir, we are listening, sir.
Hello.
Yes,
Hello, sir. Hello, sir.
Hello,
I
sir.
didn't get any response basically.
Sir, we are listening your voice,
Maybe
sir.
something wrong in my computer. I understand it. Maybe something wrong
Yes,
in
sir.
my
We are
computer is
listening.
not working. Microphone,
Yes, sir. Yes, sir.
maybe speaker is not working. Is it the problem?
Maybe, sir.
My
Yes, sir.
speaker maybe is not working. So I just remove. Could you please respond anyone? Then I can listen.
Hello, sir.
Yes, sir.
We are listening, sir.
We are listening,
We are listening, sir.
Listening, sir.
Hello, sir.
We are listening. We are listening.
Now you
sir.
listening? Hello.
Yes, sir. Yes, sir. Can you
Yes, sir.
unplug your headphones, sir?
You can hear me, but I cannot hear you. I don't know what's wrong with that.
Sir, we are listening.
Maybe, sir, somehow you press the mute button on your laptop, sir.
Hello.
Sir.
Yes,
Hello,
sir.
sir. Yes, sir.
Maybe I'm listening now.
Okay, sir.
Hello, sir.
Okay,
We are
sir.
listening, sir.
Sorry. This is actually my problem. So it's the problem is Windows 10 has a different setup. There are lots of microphone, USB audio device, context, smart audio as a system, and speaker
Yes, sir,
has a
yes.
many forms. So I don't know which form actually I'm choosing. That's why there's a problem. Sorry for that.
Okay, sir. No problem.
Okay, sir. No problem.
No
So
problem.
now it's clear. Okay, sorry for that inconvenience. So you get this point, explicit and implicit form of the function. You
Yes,
understand
sir.
this
Yes, sir.
point?
Yes, sir. Understand, sir.
So we are differentiating using these three methods only basically for the implicit form of the function. That's when you find the dependent variable and independent variable are mixing to each other. Okay. So these types of form, how can you solve implicit form in as a differential equation? You can learn many things in MAT-197. Sorry, I'm not sharing the screen now.
Yes, sir. Please, sir, share your screen.
So this implicit form, that's when we are differentiating, we are actually talking about the implicit form of the differential equation. We can solve these types of problem. And this implicit form, we can convert into a explicit form. We can modify it or we can simplify it and convert into an explicit forms. That's when the implicit function we can simplify and convert into a explicit form. It is possible, but not always. Okay, always you cannot do this because sometimes you cannot separate the variable. Sometimes you can separate the variable, you can also convert implicit into explicit, but sometimes when you cannot separate the variable, then you cannot convert implicit to a explicit function. So there are actually many forms of the implicit and explicit function, and these are actually discussed in the MAT-197 differential equation courses. But in this course, we are only talking about the ordinary differential equation, and we solve this ordinary differential equation by numerical methods, and by only these three numerical methods, that is Taylor's method, Euler's method, and Ranjikata method. And only we can solve one types of ordinary differential equation, only one type. Then solve
One
only
time.
the one types of ordinary differential equation. Types of ordinary differential. So let's make it true. So there are many types of differential equation, but in this course we are differentiating only one type, that is the types. That is the standard form dy dx f of xy. So if you find any problem which is not look like as this one, you have to convert it to make into this form. You understand? If you find any other form, then you have to convert this form into the standard form. So you can consider this form as a standard form for these three methods.
Okay, sir.
So now we have to talk about the Taylor's method. How can you solve the differential equation by the Taylor's method? Basically, we are using Taylor series method. This is not actually the different Taylor's method. This is the Taylor series method. And Taylor series, you actually studied the Taylor series in Math 167 course. Am I right? Taylor series and Maclaurin series. These are the two series you have actually learned in Math 167. I hope that you completed Math 167 because you are in 247, that you must have to complete 167. So if you complete 167, then you know that what is actually Taylor's method, isn't it?
No, sir. Sir, CC department doesn't have sir 167 codes.
So that's
Yes,
when
sir.
all department has not the same courses. Okay, doesn't matter. So basically we are using Taylor series method, not actually the Taylor's method. So I just correct the names, Taylor series method. So if you who have a experience about the Taylor series method, that's when who actually know what is Taylor series, then it is actually easier for them to understand. And who do not know, doesn't matter. I will tell you what is actually Taylor series method. And then using this Taylor series method, we solve it. So you do not have to worry about what is actually Taylor series method because I will explain it right now. So first of all, we have to talk about the Taylor series method and differentiate. And another thing, for the differential equation, there will be initial condition will be given. There will be initial condition will be given. So not only this form. So I just erase these things. Just write with the initial condition. That's mean if you find the differential equation, then it must have with the initial condition. That's mean something you need to solve these things. That is called initial condition. Initial condition will be given with that differential equation. What is the initial condition in here? That is y of x naught equal to y naught. Y of x naught equal to y naught. That is the initial condition. Y of x naught. So x naught is a domain or a point, and y naught is the value of the function. So this is the initial condition will be given. Okay. So this is the actually total problem. Dy dx equal to f of xy. This is the differential equation, and this differential equation will be given by with the initial condition y of x naught equal to y naught. That's mean the function. If you put the x naught is the initial value, initial domain, and if you put the initial domain in that function, then you will get the initial function value. So this is actually the initial condition will be given. That's one domain and one function value will be given as an initial condition. One domain and one function value will be given as an initial condition for these three types of problem. So similarly for the Taylor series method, the function types will be this one. So I just write that this one. So same things I'm writing in here. Considering the first order. Another thing is that when I say that only we can solve these types of differential equation, so you understand the order of the differential equation. This is called first order differential equation because we are differentiating at the first time, or we are differentiating only one time. That is called first order. So I'm not mentioning that first order because it is actually shown that dy dx is the first order. So you do not have to mention. So I just mention it if you have no experience about what is actually first order. So I just write it in here. First order ordinary differential equation, not the second order or third order. That's when d square y by dx square or d cube y by dx cube. These types of equation we cannot solve. We can only solve first order also. So I'm not writing first order because it is shown that this is first order. If you know the differential equation, or if you know the differentiation, what is order, then you understand. Same thing I'm just writing. These things, this condition is applicable for all the three methods, not only for the Taylor series method, also for Euler's method and Ramsey-Katta method, Rank-Katta method. For all these three methods,
Ordinary
can-
differential equation. First,
first only we can solve first order ordinary differential equation. So we consider the first order ordinary differential equation. Where is the E is given. And now we have to solve this by Taylor series. Now what is Taylor series? So we can derive the Taylor series by the total differentiation. So I'm not sure total differentiation you know or not. Do you know the total differentiation? This is also actually taught in the MAT-167. So I'm not actually deriving the whole Taylor series method. That will be actually needed more time. I'm just writing exactly the Taylor series. Okay, that's mean which method we have to solve. That's mean which formula in your term. That's mean which formula we need to solve this differential equation. I'm just writing this Taylor series. The Taylor series is of the form.
Sir, we have 1 minute remaining.
Only 1 minute remaining. So do you have class after that? So you just allow me 1 minute. I'm just writing the
Sure, sir.
equation. That's it.
Yes, sir. But we didn't give that.
Okay, so this is the last line I'm writing. This is the last line. I'm just writing y equal to y naught plus x minus x naught into y dash into y dash of naught plus x minus x naught whole square by 2 factorial that is y double prime. And then the same thing for the third one. That will be x minus x naught into whole cube by 3 factorial into y triple dash and so on, because this is infinite series plus up to double dash, that will be continuous. So this is called the Taylor series. Okay, so this is just simply Taylor series method, and we will talk about more what is actually the all of these terms, what the meaning of these things, and how can you solve the differential equation these things by using this Taylor series. I will talk about in the next class. Okay, in tomorrow. So this is up to this
sir,
class.
sir, y prime bracket close not.
I'll discuss about every terms in the next class. Okay,
Okay, sir.
because if I want to discuss this thing, that will actually need more time. What about the IoT automation?
Sir, maybe not working, sir. Automation.
I don't see anything in here. Class, routine, coding, evaluation, practical. Page start, coding to access. Automation is not working. Faculty access.
Yes, sir.
Student.
Yes, sir. Other faculties face those type.
Oh, I got it. So automation is actually upgrading. That is the problem, I think. Their CSS file is not working, so that is actually just one by one you have to find. So sharing my screen. So 247. Date is 6. Okay, so Saiful Islam,